Hi. Today, what we're going to do is we're going to talk about equilibrium constants for acids and bases. So we have what's called the acid dissociation constant, or Ka, for weak acids. We also have the base dissociation constant, or Kb, for weak bases. And it turns out the two of them are connected to each other in an interesting way. So let's take a look at how we relate those two parameters. So this is section 7 of chapter 16. And we call it conjugate acid base pairs. Okay, so to talk about this, let's take a common example of a weak acid. The weak acid that we might consider is HCN. I picked this one because it is definitely a weak acid. It's actually a pretty weak acid. But it's also a relatively simple chemical formula because, as you recall, many of the weak acids are organic acids and they have more complicated chemical formulas. So I want to pick one that's pretty simple. So this is HCN. Now, the name of this is cyanic acid. It's a pretty nasty acid. You're not likely to run across it anytime soon. It is poisonous. It's a terrible, terrible acid. Okay. So it does dissolve into water. And what we're going to do is we're going to write out how it behaves in terms of being a weak acid. Okay, remember, a weak acid will react with water. The acid will donate a proton to the water, leaving you with, now let's get the terminology here. What you get is this is cyanide is the name of this species. It's a conjugate base. Okay, and the hydronium ion, that's your conjugate acid. Okay, water is behaving as a base, right? So the hydrocyanic acid donates a proton to the water, giving you the conjugate base, which is cyanide. So what we're interested in for this discussion, and this will lead us into buffers in the next chapter, are these two species right here. We're going to write these down as HCN. And then I'll just put a little slash next to it, CN minus. And this is your acid. This is your conjugate base. Remember, the base, the conjugate base will have fewer hydrogens than the acid. That's how you tell the difference between them. The base is the one with less hydrogen. The acid is the one with more hydrogen. So those two are really related to each other pretty strongly, just through the difference of an H plus. Okay, so here's your acid, there's your conjugate base, and this is called a pair. We call them a pair because the two go together, right? They only differ by an H plus. Again, this will be important when we talk about buffers in chapter 17. But let's recall that we can write out an expression for the acid dissociation constant, Ka, right? Products over reactants. So our products are cyanide times hydrocyanic acid. Oops, I'm sorry, my mistake. Hydronium divided by hydrocyanic acid, right? Products over reactants, water's not included because it's a liquid. Okay, so there's our expression for Ka, and this has a value of at room temperature, it's 5.6 times 10 to the negative 10. As I said, it's a pretty weak acid, has a very small Ka value. Okay. Now, here's what I want to do, though. I want to point out that this is reversible, right? If Ka is small, that means it's a rather weak acid. The meaning or the significance of that is that if I take something like sodium cyanide or potassium cyanide and try to dissolve them into water, okay, I'm just dissolving. These are salts. So I'm just going to dissolve these salts into water. What are you going to get? Well, sodium and potassium salts are very soluble. So you're going to get the cyanide ion in both cases. Which is the conjugate base of HCN, okay? Now, what happens when you put those salts into water? Well, it turns out the cyanide ion will behave like a base. So the cyanide ion in either case will react with water and act like a base. It'll take an H plus. The water will transfer a proton to the cyanide ion to give you HCN and OH minus, right? Does that make sense? What we're saying here is that the cyanide is a base. It's a conjugate base of HCN, and that base will react with water if you put it in the water. So we're not putting HCN in the water, we're putting cyanide, CN minus in the water. When that goes into water, the water will protonate it, and the water will act like an acid. The cyanide will act like a base, and what you'll get is a conjugate acid here. Remember, it has more H, more hydrogen atoms than the CN minus does, the cyanide, so that means it's the conjugate acid, and then the hydroxide is the conjugate base. Okay, remember, conjugates go on the product side. Okay, now it turns out we can write out an expression for Kb here. Products over reactants. Water's a liquid, so we're going to leave that out. HCN, OH minus, CN minus. And it turns out we can calculate the value of Kb if we know the value of Ka for HCN. So I'm going to show that to you next, okay? So notice this expression for Kb is somewhat similar to the expression for Ka for HCN. They're not identical, but they're somehow similar, right? Both of them have HCN in it, and both of them have CN minus, cyanide. The difference is that the positions, whether they're in the numerator or the denominator, right? And there's another difference, which is that for Kb, we have the hydroxide concentration, whereas for Ka, we have the hydronium concentration. So in a sense, there's two differences here, right? The position of the cyanide to hydrocyanic acid, and then whether it's hydroxide or hydronium. So here's what I'm going to do. I'm going to write out both of these equations again, but I'm going to try to be a little bit more efficient in terms of the space. So there's our first one. Here's our second one. Notice they both react with water. Bases react with water, acids react with water. So this is going to be HCN plus OH minus, right? Okay, let's just make sure we have the direction of the protonation. The proton's going this way here, but here the proton's going that way. Okay. Now what I'm going to do is I'm going to add these two equations. Now this is something that's done in chapter 15, But let's take a look at what happens here. If we add these together, remember the rules of adding equations? Anything that's on the same side, you just add them together. If it's on opposite sides, you can cancel them. So if you look at it, we've got water and water on the same side here. So we have two waters. And then there's HCN, but the HCN are on opposite sides, so they cancel. There's also cyanide, but they're on opposite sides, so they cancel, right? Cancel if they're on the opposite sides. And then look at what we get with on the product. We get H3O plus and OH minus. Hydronium and hydroxide, right? That should look familiar for you. At the beginning of the chapter, very early on, we looked at this reaction here where two waters react with each other to form hydronium and hydroxide. We said, hey, that's Kw. Concentration of hydronium times concentration of hydroxide. Now, here's another thing we can say. We have a rule in terms of how we deal with equilibrium constants. Remember, this is Ka, this is Kb. And the rule is that when we add equations, chemical equations, we multiply the K values. So in other words, if you add these two equations together, the overall value of K is just going to be Ka times Kb. But wait a minute, we said that the K for the overall is Kw, so that is correct. In fact, Kw is equal to Ka times Kb. Now we know that Kw at room temperature is 1.0 times 10 to the negative 14. So in other words, that value, 1 times 10 to the negative 14, is equal to Ka times Kb. And this gives us a really nice way of figuring out the value of Kb for a conjugate base if we know the value of Ka for the weak acid. Okay, so if I say, hey, HCN has a Ka of 5.6 times 10 to the negative 10, then what I can say is the Ka for HCN times, I'll put an extra times, Kb for Cn minus, that's got to be equal to 1 times 10 to the minus 14, Kw, right? The two of them multiplied together have to be equal to Kw. So if I know that Ka is 5.6 times 10 to the negative 10, and I know that that times Kb is 1.0 times 10 to the minus 14, then that's pretty easy. Kb would just be 1.0 times 10 to the minus 14 over 5.6 times 10 to the minus 10. And there you go. You've got it now, which I think is somewhere around 1.8 times 10 to the minus 5, I think. You can check that on your calculator, but I think that's what it comes out to. Okay. So very interesting result here. Ka for a weak acid times Kb, its conjugate base, is equal to Kw, which is 1.0 times 10 to the minus 14. So let's take a look at an Aleks problem. Deriving Kb from Ka. Complete the table below. Round each of your entries to 2 significant digits, and you may assume the temperature is 25 degrees Celsius. So notice what they do here. In the first one, they give you the chemical formula for an acid. They don't tell you what the name of the acid is. Looks like it's acetic acid. Then they give you the value of Ka, 1.8 times 10 minus 5. Then they want you to write the formula for the conjugate base, and they want you to calculate the value of KB. We now have a method for doing that. Likewise, we can go the other way. If we know the formula for the weak base, the conjugate base, we can find the formula for the acid that is associated with it, as well as the value of Ka. So let's take a look at this example. Okay, so let's start off with the first one. The first one, they give us the formula. I don't really like the way they're writing this formula out for acetic acid. Okay, now let's write the formula for the base. So this is your acid. So let's write out the formula for the base and then calculate the value of Kb. Okay, it's pretty simple. What you do when the acid becomes a base is you lose an H+, right? The H+ is reacted with water, goes into the water. So you lose that H+. So all we got to do is remove an H+. So the reason they wrote the H out here on the left is just to tell us to remove that one. So we just need to remove that H. However, because we're losing an H+, remember that H+ is positively charged. This is now going to be negative. So we're going to write a negative over here, CH3CO2 minus, right? Now the value of Kb, pretty simple. We have this relationship, Kw is equal to Ka times Kb. So Kb would just be Kw over Ka. So 1.0 times 10 to the minus 5 over, oops, sorry, I got that wrong, minus 14 divided by 1.8 times 10 to the minus 5. And I think that comes out to about 5.6 times 10 to the minus 10, if I'm correct. Okay. So let's take a look at the second one. The second one, now in this case, they give us the formula for the base. Remember we said that very often the weak bases are the ones that have a nitrogen atom, right? The hydrogen, the proton goes on to the nitrogen. And here they give us the value 1.7 times 10 to the negative 9. Okay, so let's figure out the formula. We just have to pop a hydrogen on there. So I'm just going to write HC5 NH5N, or we might, and it's H+, right? We got a plus there. Sorry, it's H+ we're adding. Or we might write it C5H6N plus. Again, you're adding an H+, or C5H5N H+. So, there's different ways you could draw this out. You could write this out, but all three of those are, none of those are incorrect. Okay. So if we want to figure out what Ka is, Ka, again, we're using this as our relationship here. Ka would just be Kw over Kb. So that's 1.0 times 10 to the minus 14 over 1.7 times 10 to the minus 9. And, I'm not really sure what that is, but let's go ahead and grab a calculator and figure it out. So 1 times 10 to the minus 14 divided by 1.7 times 10 to the minus 9. And it looks like it's about 5.9 times 10 to the minus 6. Okay, there's our second one. We have one more where they give us the conjugate base formula, CH3 NH2. That's methylamine. It has a Kb value of 4.4 times 10 to the minus 4. Okay. So again, all we got to do is add an H+ to it to get the acid. So CH3 NH3 plus, right? It's going to be positively charged as you add an H+. Kb A again would be KW over KB. And that would be 1.0 times 10 to the minus 14 over 4.4 times 10 to the minus 4. So let's see what that looks like. 1 times 10 to the minus 14 divided by 4.4 times 10 to the minus 4, 2.3 times 10 to the minus 11. Okay, interesting relationship. Now here's what's going to happen. When we get to the next chapter, chapter 17, what we're going to look at is something called the buffer equation. And the buffer equation is going to give us a way to calculate what's called the pH, which is equal to the pKa plus the log of the concentration of the conjugate base over the concentration of the conjugate acid. Okay, so this ratio of the conjugate base to the conjugate acid will be important. And the pKa, figuring that out, we'll talk about that in chapter 17, is related to this discussion that we just did here. All right. Simple calculation, but a lot leading up to it. Take care.